or an instance of how you improved this yield? Like, could you discuss one particular instance where you improved process yield and like through this method?
Yeah, typically when you make a new silicon product, the initial batches usually have some kind of uh, the design is usually on the edge in some areas where there are failures. For example, in case of image sensors, there may be many sensors that have a bad line going through it, or a whole bunch of bad pixels that are not usually present. So when this happens, the yield on of good sensors drops, and it's not profitable for the company to continue making that until we fix the problem. Uh, Fixing the problem on integrated circuit chips is it requires it requires a lot of failure analysis, and there are specialized labs that can do some testing for you, but you have to guide them and tell them where to look and what to look for. So
Right.
um, yeah, so that is an activity that I have to do whenever we start testing a new product, and if we see a certain kind of failure that is not expected. So
Right.
yeah, so there are
And you work
labs
with
here in San Diego and in Irvine and in the Bay Area that we work with, and we have to first do experimentation on our own to kind of localize the defect and figure out where the defect is on the chip, and then we go to these labs and we tell them where to look and take pictures using scanning electron microscopes or other methodologies, and then we go back to the foundry that makes the sensors and tells them that we have a problem in this area, so they should fix their process and improve the yield for us.
so do you have like a percentage of this, like you improve yield by this percent, like any instance we improve this yield by this percent, so
Yeah,
like
so the last time we had a problem in which we had to go back to the foundry after failure analysis, our yield was down at like 30%. And then after we did the failure analysis, went back to them, then we improved the yield to about 70%. So the yield
okay,
went from around 30% to 70%, and 70% for a chip this size is actually fairly good.
yeah, so
So
that's like a major improvement in yield, like you more than doubled the yield. That's nice. Okay.
yeah.
All right. um, let's see. Is there any other, by the way, is there any other instance where you like had an even greater impact on the yield other than this?
Um, this was the largest one. I mean, we have other,
Okay.
sometimes we have defects which take about, say, knock out about 10% of our yield, and it's usually sometimes the foundry itself is going through process changes, and that's why we have temporary dips in yield. But
Yeah,
they normally don't require that much failure analysis on our part. So
I understand. I understand.
yeah,
Okay.
yeah, I think for mentioning one example is probably enough.
Yeah. Okay. Right. I was just like wanted to make sure that this is like the best figure we could present there. Okay.
Yeah.
You also said that you architected a custom FPGA based image acquisition system to allow wafer probing of state of the art images.
Yeah. So yeah,
Uh,
so that yeah. Um,
so how did this benefit the organization? Like this particular thing?
Sorry, yeah, I was actually in my car. The went on to that system. Okay, yeah. So as I was mentioning earlier, that the testers that are available in the market usually don't work at the data rates that we require. So we had to engineer a custom solution that would work on the existing testers. So we made this board on which we plug on two FPGA boards that gather the data from the sensor and then slow down the data rate and push it to the rest of the testing system. So that was a solution that I architected and led the deployment of before we started testing our current batch of sensors.
All right. Okay. And okay, so this was like helped you test your like new product, right? Like an emerging product that
Yeah.
you had.
So if we hadn't done this, then we had no way of testing the sensors at wafer probe, and that would have been a problem because now you have to basically blind package the sensors and then just test them once they're packaged, and that cost the company a lot of money.
Okay.
So if you want, I could probably work out a dollar figure on this. Uh,
All right. Like how much you
I'll have
saved
to
by developing this, right? How much money you saved?
yeah.
Okay. So
I
like
can work that out. I can email it to you.
right. Okay. And like if you don't email it to me, I can leave the space for it in the resume. All right, and you can fill it out later.
Okay.
All right, and highlight that so you can fill it out later. Okay.
Mhm.
And let's see. Currently driving. Okay, so you also said that you are currently driving the development of next generation SoC based image acquisition system for wafer probe, resulting in faster test time and minimizing package part yield loss. Right? Could you please
Yeah.
like elaborate like how you're contributing towards this development, like exactly what your contributions are over here, and like by what and like could you like elaborate the results here a bit more, like by what amount is this expected to reduce yield losses?
Yeah. So, sensor testing happens in a couple of two, three phases basically. So the first thing that happens is wafer probe that we've been talking about. And then once the wafers are probed, then the good parts are packaged and put onto PCBs, and then we test the PCBs, and there's some fallout over there, and that fallout usually happens because the wafer probe system is not robust enough or not fast enough so that it can test every aspect of the sensor that we want. There's more testing that we can do when the sensor is actually on the PCB. So the idea, and those are because of built-in limitations of these testers. So the idea here is that we take the camera system, basically. The camera system is based on an FPGA, and we implement that whole camera or parts of that camera system onto an FPGA that is working on the tester itself. And that way we can do almost all the testing on wafer probe that we will do once the sensor is inside the camera. So that should give us more test coverage. So if, for example, currently we are able to only test for about 70% of defects, once the system is in place, then we should be able to test by around 95% of all defects. So uh, what that is saying is that currently we're testing for about 70% of defects, so we expect 30% of parts to fail when they are finally put on sensor on PCBs and then tested the second time. That
Right.
figure is going to go down to 5% when we implement this system. So
Okay.
since once you put the sensor on a PCB, there's more value added to it because it has gone through a number of other steps and there's value of the PCB itself. There's more money wasted if you fail it later on in the process. So if we reduce the failure rate at PCB level, then we save the company a lot of money.
Okay, and like could you estimate like how much money is this expected to save? Like,
Uh, since this has not been deployed, I mean, it's still being worked on. I can think about it. Yeah, it
okay, all
depends
right.
on how much of the product we're going to sell, right? And I don't want to um, like put a dollar figure on that yet,
Right,
or
right, right.
or
I understand.
reveal how much our sales are because that's also proprietary information.
Right. I understand. Okay. All right. So moving on to some of the projects that you've done as a principal engineer. Okay.
Hmm.
So you designed the lead for so you were the design lead for FPGA based autofocus development platform. All right.
Yeah,
So how did this platform like how did this platform benefit the organization, your organization?
yeah. So we have a a goal for us for this year, and that we so okay, let's go back. There is a technology called phase detect autofocus, which is present in a number of cameras that are out there in the market, but we've never had it in our cameras. And the all the technology and the intellectual property around it is quite proprietary. So it's not something that you can just buy. So it has to be developed through R&D in-house. So we had a target for us for this year that we want to implement this new technology in our cameras. So we needed a, a development platform that we could use to do the R&D. And then once we have a decent idea of how it's going to work and what the algorithm is going to be, then we will implement it in the camera, which is has been announced and it's going to go in production early next year. So and it's a key feature of the next product that we have announced. It's one of the features that is being used to market this camera. So
Right.
my contribution here is that there is so the algorithm can be developed in software, but you don't know how it's going to perform unless you put it in real hardware and test it out. So my challenge here was that I had to develop an FPGA-based system in which the algorithm that is being written in a high-level language like MATLAB can be translated into a hardware language like System Verilog and implemented, and then also provide enough flexibility to
Sorry,
the
could you repeat that hardware language like into a hardware
like
language like System
System
Verilog?
Verilog,
Okay. How do you
yeah,
spell that?
Verilog.
Verilog.
So
Okay, thank
system
you
is
very much.
system and System Verilog. Yeah.
Right. Understood. Go ahead. Like, you were saying something about flexibility.
Yeah, so the system needs to. I mean, it's the algorithm is specified in hardware, but it needs to be flexible enough so that those who are doing the development of the algorithm are able to change it uh, on the fly,
Mm-hmm.
instead of having to go through a whole compilation effort of changing the hardware every time. So
Okay.
so that platform is something that I'm working on right now, and it's going to be instrumental in implementing this technology in our next camera.
Right. So essentially, this also improved like the user experience of it, right? Now the technology will be
Yes,
more flexible. They can use it however they want, right? It's like
yes,
FPGA based. Okay.
yeah.
So I understand how this is more flexible now, but how does it optimize resource utilization and latency?